This summer, I worked in the Laboratoire Charles Fabre at the Institute d'Optique Graduate School studying attosecond electron wave packets. Modern physics has become very interested in understanding the quantum nature of reality. One way in which scientists can probe quantum regimes is through experimental attosecond physics. Attosecond light pulses are some of the shortest flashes of light ever produced, and when they are focused on a gas, they ionize atoms or molecules, freeing photoelectrons in the process. These photoelectrons can be thought of as matter wave packets which behave in a quantum mechanical way. During my internship, I studied these wave packets in the context of a time-of-flight experiment. In this experiment, photoelectrons propagate through a 2-meter tube from initial ionization up to a microchannel plate detector. The wave packet's propagation in free space is pretty trivial, but a potential barrier can be applied during the wave packet's propagation and produce matter-wave interference phenomena. Up to the point of my arrival, my group has been unsure about the particular effects an applied potential has upon the wave packet's subsequent propagation in the experiment. In particular, we wanted to know whether quantum interference and diffraction patterns would still be measurable at the detector at the end of the time-of-flight tube. In order to try and better understand these questions, I performed both numerical and analytical modelings of the wave packet's propagation. Trying to simplify the problem and gain an intuition for it, I first performed my simulations working under classical and semi-classical approximations. I then moved on to a fully quantum treatment where I analytically computed how the wave function describing the photoelectron evolves during the course of the experiment. Further work needs to be done on this project to fully model the photoelectron's propagation in the time-of-flight tube. However, if one day successful, this experiment could have really interesting implications for the landscape of quantum mechanics, including things like exploring non-locality among other ideas. I would like to conclude by thanking everyone who made this wonderful experience possible this summer.